Welcome everybody to this discussion paper seminar, webinar actually, about model uncertainty and missing data. It's an objective Bayesian perspective, and it's a paper jointly written by Gonzalo Garcia Donato, María Eugenia Castellanos, Stefano Cabras, Alicia Quiros, and Annabel Forte. And it's a great pleasure. It has been a great success. Actually, we got a lot of contributed discussions and also great invited discussions. And I hope it will be a great event and you all will enjoy it. And start immediately by passing the floor to Annabel to introduce the seminar and also to say a few words about Maria Eugenia, who sadly passed away just while the paper was in progress, almost accepted actually. So Annabel, floor is yours. Thank you very much.
So thank you very much, Igor. Hope you can see my screen. So I will start by thanking Igor for all the editorial work, and also to Julia and Arbel for putting together this webinar. And well, before starting the presentation, as Igor just mentioned, I would like to talk a little bit, to take a moment to honor the memory of our dear colleague and co-author, María Eugenia Castellanos. So María Eugenia was not only a brilliant statistician, but she was also a generous mentor, a kind collaborator, and a true friend. She earned her PhD at the University of Valencia under the supervision of our also beloved and deeply missed Susi Bayarri, and she had become full professor of statistics and operation research at University Rey Juan Carlos in Madrid. Her work combined intellectual rigor with kindness and enthusiasm, and she made important contributions in objective Bayesian methods, model comparison, variable selection, and the analysis of extreme data. And she held visiting appointments at Carnegie Mellon University, the Federal University of Rio de Janeiro, and the University of Cagliari. Beyond her scientific work, María Eugenia was deeply committed to the statistical community, and she served as an associate editor for Bayesian Analysis, for statistical methods and applications. And she was an active member of ISBA, IBS, and also the Spanish Society for Statistics and Operation Research, and the Spanish Biostatistics Society. She also helped organizing several major conferences, including OBASE 2015 in Valencia and the Spanish Biometric Conference in 2021 in Madrid, always bringing energy, warmth, and precision to everything she did. Her scientific legacy lives on through her publications in statistical science, Bayesian analysis in biometrics, or statistics in medicine, among others. And perhaps more importantly, to the many students and colleagues who were inspired by her generosity and passion for research. We are truly grateful to have shared this journey with her, and we really think that this discussion has been a lot more difficult without her being around. We dedicate today's presentation to her memory, and we would like to say thank you. We miss you, María Eugenia. And now, let me briefly outline how today's session will unfold. So first, I will pass the word to Gonzalo Garcia Donato, who will introduce the main motivation and conceptual ideas behind our work. Then we will move to Stefano Cabras, who will guide us through the methodological developments and some key theoretical contributions of the paper. After that, I will return to present the numerical experiments and empirical results. And then we will give the floor to our invited discussant. So Igor will give the floor to Merlise Clyde, Marco Ferreira, Alexander Lee, and Javier Rubio. And finally, after that, Alicia Quiros will close the author's part of this session with a joint rejoinder, responding to some of the points raised during the discussion. So now, to begin this presentation, I will hand it over to Gonzalo. So whenever you want, I will stop sharing. Please go ahead.
So thank you, Annabel. Hope you can see my screen. thank you everyone for joining us today. Difficult moments to start because it's difficult to start this talk without having María Eugenia here. But anyway, good afternoon to everyone. Let us begin this talk by discussing the foundational concepts and, more importantly, the principles that guided the development of this research. I think those are important to understand what is being done in this research. So model uncertainty, what is model uncertainty is one of the primary concepts here. So you have data, D, but then for that data, instead of just having one model, you have several models that have been considered. Those are going to be denoted as F gamma, and gamma is the index that is going to identify the different models. Notice that all models, every model has its own parameters. And particular problems within model uncertainty are testing, hypothesis testing, variable selection, and model averaging. All these particular problems are treated either more explicitly or implicitly in this research. The second main term is, of course, missing data. So as a researcher, you were expecting to receive the whole data set D, but then suddenly part of that data, D1, is not available. You don't see that part of the data in your data frame. And then you have to proceed with the remaining data, which is going to be here denoted by D not. A few words about the perspective. Of course, this is a Bayesian talk. This is a Bayesian paper. And we identify Bayesian inference in this paper as probabilistic inference. So we aim to derive everything here that can be understood and can be obtained just using probabilistic rules. So our main point is to derive the posterior probability of each of the competing models given what you have observed. Just a small observation of this connection between Bayesian inference and probabilistic inference. I don't know when we lost that name of probabilistic inference to embrace the more modern Bayesian word, but this is not new, calling what we do probabilistic inference. Notice that even Jeffries in his book, first edition in 39, the third edition in 60-something, 63, he didn't use the word Bayesian just a single time. And he decided to title his book Theory of Probability. That's why the main here idea is that he was aimed at producing inferences that were based on probability. This is what you are going to see here, just probability. The third aspect that you have to notice in this paper is that we follow an objective-based approach, in the sense that the methods we develop are obtained just using mathematical rules and statistical arguments. And we plan to obtain procedures that are fully automatic for the final user. In the following sense, you just need to press the button and you will obtain the results. And we are going to give you arguments so that you can trust on that numbers. There are many various ways of approaching method using objectivity, but we follow two main ideas. First is the criteria in Bayesian and others paper, where these authors, they present several criteria that can guide to specify the prior distribution that you have to use. And also the G priors that were presented by Cerner and Xiao based on the seminal idea by Jeffries in 61. It's not only the idea of using the G priors, that you will see several times that concept of the G priors, but also the idea of using a prior for the new parameters that is centered on zero. That was like a revolutionary aspect. And then also to use the information matrix to obtain the variance covariance matrix for the priors. Those are the main elements that you will see that have inspired part of this work. And with all these ingredients here on the table, the object on which we are focusing on this is the marginal. Why? Because that has a very clear probabilistic definition. I was teaching the other day, 2 days ago, the first degree of probability, and I was introducing in random vectors the idea of what is a marginal. It's something that lives in the probabilistic area and is very easy to present. And the marginal for the model gamma evaluated that the part of the data you have seen is just integrating now the joint marginal for the unknown variables that you haven't seen. That's pretty simple, and then you don't have to invent anything. You cannot do so, for instance, with the Bayes factor, because the Bayes factor doesn't have that clear probabilistic definition. Once you have the marginals, then you just apply the Bayes rule to obtain that the posterior probability of each of the competing models given the observed data is the marginal times the prior divided by the normalizing constant, or expressed in terms of the Bayes factor. If you divide by the marginal of one fixed model, is the Bayes factor times the prior divided by the marginalization constant. Well, we started this research like 4 or 5 years ago, and it's very difficult to start working on missingness without thinking on Rubin's rules, because those are ubiquitous rules that they're almost in every paper that speaks about missingness. So we started thinking that the possibility of just solving that problem in 1 week. I mean, the only thing you have to do is to complete your datasets. Imagine that you have the way of computing the posterior probability of the competing models given the complete dataset. Then you have your preferred approach, you have your software for that, and then the only thing you have to do is to obtain several complete datasets. And once you have complete datasets, you have imputed, then you just compute the posterior probabilities of each of the models. And to obtain the posterior probability given what you have observed, the only thing you have to do is to average over the complete datasets. In principle, this is very convincing. You write several pages of that, and everyone is going to be convinced that this is going to work. The problem is that this is not that clear in the problem with model uncertainty, because notice that I have started speaking about this, saying that we can obtain capital J, different complete datasets, but from where I'm going to obtain these datasets, because I don't know which is the true model. So that enters into conflict on the idea that we don't know which is the dataset. In a sense, that's something we have formalized in our paper, where we see that, in a sense, what you don't know appears in both sides of the equation. So you can invent something else. We will later see that there are parts of our research that has reminiscences on the Rubin's rules, and they have like that interpretation. And that's the second part I'm going to talk about, is the core. I will speak mainly about the models and few highlights about the research. We have focused, although we try to speak about general ideas, we are trying to focus on regression models. And in regression models, you have Y is a dependent variables, and then you have X1 to XP. Those are regressor or independent variables. And then you have M, which is an N times 1 plus P binary matrix that is going to contain, with the ones, is going to contain the cells that are going to be hidden to us. The models we consider have this form. Notice that equation 2 is the regression part. That's the normal part that appears in all the studies about variable selection in regression. That tells how the models differ on how the different possibilities about the X's act on the Y's, or even what is the form of the errors or the leak function. So what is important in equation 2 is that you see the gamma there. So that is where the competing models differ. While 3 is the equation for the X's. First is that you realize that when you treat the problem of missingness, you have to think on random variables, on the idea that the X's are random variables. So that changes the paradigm where you think where the X's are dependent. Here you are forced, in a sense, to think that the X's are random. And that's 3 is the model for that X's, for those X's, that depends on nu. You will later see that we call that model the imputation model, although it's not that accurate, because this is not for the Y's, it's only for the X's. Important thing to notice here, in what is going to be derived later, is that part, equation 3, doesn't depend on gamma. So all models agree on that part of the model. They agree on which is the distribution of the X's. Finally, 4 is the distribution of M. Recall that M is a binary matrix containing ones and zeros, and that model says why in some parts of the matrix M appears ones and why in other parts appears zero. That's simply the model for the M. Once you have the M, someone hidden to you those cells containing the ones in the M. So at the end, the observed data is D naught, using my previous notation, containing Y0, X0, and M with an obvious notation, while the not available data is D1, Y1, and X1. What do you think to do? It's just integrating now everything that you don't know. That's the expression here, is the integral of the joint distribution written that way. And then the only thing you have to do is to integrate everything you don't know with respect to the prior. Of course, the prior is something that is going to be crucial in this research. You cannot use the X's there, not only because the X's are not available, which is true. That was our original problem with Fellner prior, or even in other priors that use a normalization or scale the coverage. You cannot use the X's because they are not known, but also because that formula doesn't allow you to use the X's there. So it's not legal from a probabilistic perspective. And we discuss a lot about that ingredient in our research. And that's part of the highlights of the paper I'm going to introduce you. So what do we do in this paper? What you are going to see in the rest of the talk. So we studied the role of the missingness mechanisms, that distribution of the M, and the conditions under which you can just ignore, you can just forget that distribution. We propose objective priors for random X's. The good thing with this is that you have to think on random X's, and if you do so, as a reward, you obtain priors that work on the missingness problem, but also priors that are more general, that are different even from the priors that people are using, and that's something we are working in. For this research, this prior circumvent, they need to have the X's available, because you cannot use, for instance, the X transpose S because you don't know the X's, but that affects also other priors that use this scale to produce priors. We identify aspects of the solution that can be interpreted in Rubin's rules fashion. In summary, those that depend only on the X's. And then once we have presented all the general results, we apply everything to variable selection in the linear models, and also to a different problem, which is choosing the distribution of the errors, like two specific problems on which we apply our methodology. But this is going to be part of Stefano part of the talk. Thank you.
Okay, thank you, Gonzalo. Yeah, what I will do, I will illustrate some general results. Some of them are really general, others are mainly focused on linear regression. So the first, following the highlights of Gonzalo, is what happened with the missing mechanism, why it is ignorable. The idea is to reach this factorization by separating the model of interest by the missing mechanism. This can be done by stochastically separating the parameters that are for the model, theta gamma, from the parameters that regulate the missing mechanism. Yeah, how can we do this? We have two key conditions. First of all, we will assume missing at random, and we will assume missing at random. So the missingness depending only on the server data. And again, we assume a priori independent the model from the parameter by the model from the missing mechanism. If, and thank you to this, the missing mechanism is ignorable, then the marginal that Gonzalo talked can be just a function of the observed data and no longer of the missing mechanism. With this in mind, we can calculate this marginal by integrating all unknowns of basically the missing mechanism and the parameter of the the imputation model, the equation 2, with respect to its posterior. Now, where this marginal, this conditional marginal is just the marginal we will calculate once we have the x1 and the nu. So this is, in some sense, a way of interpreting this procedure in terms of Rubin's rule that suggests basically this, that it is not totally justified from a probability perspective. For example, procedure like I impute the missing, and then I calculate a base factor. I impute the missing, and they apply whatever procedure for complete data, and then average over that. That is not totally justified according to what we developed. So again, the above integral just suggests this Monte Carlo approximation for the marginal. This one will be the object that we will use to approximate the marginal that will be using the base factor. So essentially, we draw the imputation parameter nu from its posterior, and then we draw missing data. So general consideration about prior that we use. Basically, the prior for the model parameter, so here for theta gamma, is for the specific parameter for the model, we have a common parameter, which are alpha and nu. These are common to all gamma model, and a specific model for specific prior for the gamma model. The common parameter can be improper because they are normalizing constant, pseudo constant, just simplify into the base factor. But the model for the prior for the beta gamma has to be proper. The idea is this. Then we have to look at which is the suitable prior for beta gamma. So now focus on, and now we have to move to a specific situation. For example, in a regression. In a regression, we have to compare the null model, just the intercept, against a model in which the columns of the X matrix are indexed by gamma. So now X is random. It's random as some multivariate distribution from which we at least require to have a mean because we have to center the X. And the possible equivariance matrix. All these parameters, mu and sigma, are regulated by the new parameter. So the idea is to derive the prior, the beta gamma prior for the specific parameter, using again the efficient information matrix of this likelihood. This is the likelihood for that take into account the fact that X is also random. This leads to a prior similar to the G prime, that we denote as G prime prior, in which the variance covariance matrix that can be calculated with the full data now is substituted with this sigma gamma gamma. What is the corresponding block for the corresponding covariance of the imputation matrix sigma that we illustrated above. Note that this sigma is reports a variance covariance matrix that is usually inflates with respect to the X transpose X using digit prior. That's because the X are run. But also another thing is that this one cannot be calculated if we see data, but our sigma gamma gamma is always defined, even with the p greater than n. Now, the corresponding base factor is just the average over this, and the average is taken considering the posterior distribution of the missing and nu. In this moment, now appear the imputation model, because this the posterior here depends on the specific imputation model we choose for the X. Another example we will treat is the case of heteroscedasticity. Now, in the case of heteroscedasticity, keep in mind that X is fixed, so there is no question about which column of X has to enter in the linear model, just that we have some uncertainty about the variance covariance of the error. Basically, these H here are multivariate probability function that are symmetric about the origin. So for this model, for the common parameter, which are the intercept, the beta 1 and sigma, we use the right arm measure that is the prior corresponding to this class of model that share a common variance graph with expected transformation on location and scale. And also the common parameter are evolved with the same dimension or on the two model. And again, they are and also DH is symmetric. So for testing the typical problem in heteroscedasticity, we want to test if, for example, the error are independent against some structure in the covariant matrix, which is assumed to be known. So I is the identity and phi is a known matrix. Once we have this and we apply all the machinery we illustrated, the base factor, keep in mind that now is the ratio between two expectations. The marginal in the numerator for the null for the null model, and the marginal in the for the specific model for the model 2. So here we can see that expectation appear numerator and denominator, and for example in this case it is clear that the base factor we have to use is not an average base factor over some imputation mechanism. So these are the two main general results that we have in the paper, for which we illustrate all the previous concepts. Now I move to Annabelle that will present the numerical experiments.
So thank you very much, Stefano. So I will now introduce or show how our method works in some specific scenarios. And in particular, I would like to say that in the paper and in the supplementary material, we have a total of 5 experiments from which I will present 4 today. And these are simulated and real data examples. And 4 of them, the first 4 are related with uncertainty on the regressors in the linear model, as Stefano just presented. And the 5th one is related to the competing error structures that we just showed. So here, I must say that the imputation model that we have used, and for this imputation model, I mean equation 3 that Gonzalo presented before, is a multivariate normal model, and we are going to compare with what we call the Oracle GVF, which is with the full data, because in all the cases we will have the full data set and we induce the missing mechanism. And then we're going to compare also with the least wild election. Will happen if we use least wild election and then we have a smaller data set and we use the G-base factor. And also for experiment 1, we also compare our method with SIAS as another method from Young et al. 2005. And if we move to the first experiment, here is a simulated experiment, and it's based on the simulated experiment on Young et al. 2005. And here we have K potential regressors, K equal to 10. We have different correlation between these regressors, so these variables, and we induce both missing completely at random and missing at random mechanisms of missingness in the data. At the end, we have a 40% or a 65% of missingness in the data sets. For all of these scenarios, we do 100 replicates, and I will say this, and this is for all the examples, when we do missing at random and we induce this missing at random, we will use the impute function of the mice package in R. Then to measure this in this first experiment, as I said, we will compare the Oracle, the least weight election, our method, and also the SIAS. And we are going to use, apart from the regular matrix, we are going to use the signal to noise ratio summary, which is a ratio between the sum of the inclusion probabilities for the variables that are really included in the model and to the ones that are not included in the model. And what we can see is that our methods usually show higher specificity and sensitivity. If you look at the blue squares, you can see that our method always have a larger probability for the variables that are really included in the model. And also it shows less variability, as you can see in the purple squares, in most of the cases. And then compared to CS, what happens is that it's outperformed even for our method, of course, as you can see in the green squares, but also by least wide election. Okay, so then we move to the second experiment. This is a well-known data set, the Ocean data set, that is a real data set from which we have 7 covariates. This is a sample size of 178. And here what we have is that we induce missingness at 10, 20, and 30% per variable in variables from x's to x10. And we do 1,000 replicates for each scenario. I must say that here, as well as in the previous experiment, the multivariate normal imputation model makes a lot of sense because all the variables in the setup are continuous variables, so it makes sense to use it. And what we obtain here is, you can see in green the dilation method, in blue our method, and then the red dot will be the oracle, like with the full data set, the inclusion probability for these variables in the full data set. And what we can see in general is that our method preserves the oracle evidence better. You can see the blue box plots always closer to the red dot. It shows also less variability, and it fluctuates less than the green one, which is the dilation one. And well, so if we move to the next example, which is in the supplementary material, here we have also a well-known data set, the Boston housing data set. And what happens here, different from the previous one, is that we have 2 out of the 5 amputated variables. So because we have a total of 13 variables, but we amputate 5 of them. And in those 5, there are 2 of them that are clearly non-Gaussian. So we wanted to test what happens if our imputation model is not really according to the variables that we have. And then what we observe is that in green, you can see the square for those variables, and we can see that we have a slightly worse behavior from our method, because in that case, we are losing more information when we use our method, but in all the rest of the cases, it worked better, as we show in the previous experiment. So it makes us think a lot that we have to take special care when the variables that we have are not, in this case, they're not normal or they're not Gaussian. So we have to take a look on the imputation model and take care of those. Despite in our method, we just use this multivariate normal in the examples, because our method is thought for any kind of imputation model, any possible imputation model in general. But here, for this case, it's not working well. So the last experiment that I will show is just this one, which is comparing error distribution, the heteroscedasticity. And the synthetic data that we use is inspired by the advertising dataset in James et al. 2013, where they were studying product sales in terms of the budget for radio advertising. And also what we are trying to test is if the error term is based on an homoscedastic or an heteroscedastic covariance matrix. And this heteroscedastic covariance matrix will depend on TV advertising budget. Again, we induce missingness in different scenarios. And what we observe here is that in any case, in any scenario, our method is always closer to the oracle one. And it's true that the chosen model will be the same in most of the cases, but our method is less variable and is closer to the oracle. So having said that, let me conclude with some remarks. So we have developed an objective Bayesian framework that unifies uncertainty and missing data. So the uncertainty for the model and the uncertainty for the covariates in the missing data. So we propose an imputed G prime base factor, which generalized Selner's G prior to incomplete variable covariates. And across all experiments, our method generally preserves oracle evidence and is more effective than the lection and less variable than the lection. Still, several questions remain open. As I said, the flexibility in the choice of the imputation model, the connections with predictive performance or other uses of the models, and these and other questions were carefully considered by the discussant, to whom we really express our sincere gratitude, and we invite them now to share their insights. So thank you very much for listening, and Igor, whenever you want.
Thanks a lot, Annabelle, and thanks for the great presentation to all of you. It's been very nice, and also thanks a lot for being on time, which is great. And so I just leave the floor immediately to the first invited discussion, who is Merlise Clyde.
All right. Okay, thank you.
Thanks a lot, Merlise. So floor is yours.
All right.
Thank you.
Okay, can everyone see that? All right. Well, thank you very much for a wonderful paper and chance to discuss this. I'll just start off with just kind of a very brief summary. Kind of the key point to the talk is to really focus on looking at the marginal likelihood calculation, which really just depends on the observed data, not the missing data, where we've integrated out all of the unknowns in here from a kind of a, again, probabilistic framework. One point that is, I think, kind of key to realize in what makes this more efficient is basically they're using a Rao-Blackwell-Eyes estimator to compute this marginal likelihood. So if one reads through missing data, say, for example, in the book by Peter Hoff, then, of course, you might think, oh, why aren't we using the Y's in terms of the imputation? But we really don't care about necessarily the missing X's. Those are nuisance parameters in a sense. And so this framework allows us to actually integrate them out, which should, in principle, reduce the kind of Monte Carlo uncertainty in those final estimates of the marginal likelihoods and hence Bayes factors. So as opposed to doing a full-blown Gibbs sampler. I guess one of the questions that one might have is really how does this scale up to larger model spaces? And so from what I could tell from the examples in there, everything is being done under this kind of framework where we can actually enumerate the models. And so in computing posterior probabilities and other quantities, we're actually summing over all of the potential models in the model space. Of course, one thing that's a really valuable point about the Bayesian paradigm is that we do not necessarily need to enumerate for large P. We can still use Monte Carlo or MCMC sampling to actually sample over the space of models. In that case, though, we no longer want to use again the quantities that are up there where we're summing only over the observed models. And so one question, and this kind of also relies even to the finite dimensional case where we can enumerate, is what's the proper framework to do? Should we do MCMC over the model space with the marginal likelihoods using common imputations? And so again, the imputations there would be both the missing data and the unknown parameters, say new, or do we do a joint MCMC where it's still in this kind of successive sampling framework where we generate the missing data conditional on V, be conditional on the observed x's, and then propose a model and do kind of an accept-reject step along the way. Okay, so there's, again, there might be some benefit by using common imputations that don't depend on the model given the framework. Of course, there are other challenges of sampling a high-dimensional covariance matrix for large P. And so that might open up the question is, should we also do selection in the covariance structure for sigma, as well as the selection of what x's go into the model for y? Okay, and so this, in some sense, not within the missing data context, but in general, selection for graphical models has been well studied by a number of authors. In that case, we might still consider a joint distribution for the y, the x's that are in our model, and then the x's that are excluded from the model. And so, at least under the framework here, this all has a multivariate normal distribution conditional on the parameters. Of course, the graphical model is going to explicitly determine that conditional independent structure with edges between variables that are connected. Now, in the framework for the current paper, all the variables in both, whoops, there was a typo there. So both in the x in the model and x without the model are actually completely connected. So there could be some benefit in high dimensional cases of trying to represent, say, that there are simpler structures in that covariance matrix. Okay, and so you could relax the assumption and consider selection over the larger graph space. And so in particular, a paper from 2009 in Carvalho and Scott, they actually looked at hyper-inverse Wishart priors for graphical model selection. This is also done from a kind of objective viewpoint where there are, again, reference priors or improper priors placed on the covariance matrix, but are using fractional Bayes factors to get around that kind of ill-determinedness of using improper priors when the dimension is changing. And so actually one thing that's kind of interesting in that framework is that if you then look at what this prior induces on the covariance for in the regression for y given x, that actually reproduces the kind of classical G prior, where the covariance in the prior for the betas given the x's depends on the x's as opposed to the sigma. So it's another alternative kind of justification for perhaps using the G priors in this setup. Of course, there would need to be extensions to handle sampling for missing data in this context. Again, that perhaps could be done in this two-part where one is generating the missing x's, but conditional on this graphical model structure and just dependent on the observed data. One of the big things, though, with looking at priors on covariances is that one has to, again, there are lots of variations in what those priors are, lots of opportunities there for different priors, and of course, what are the sensitivities of those priors. I'm probably over time, but just one last point is that the advantage of this, the imputation G prior, even if you don't have missing data, is that it removes that dependence on the observed X in defining the covariance matrix. Of course, there are some disadvantages of that. Computationally, it's going to be more expensive, so one may not want to use this, even if one does have complete data. There's the issue of joint normality if we have constructed variables. So, for example, in the well-known ozone data, there typically are interactions and quadratic terms. And so, of course, using the covariance matrix in defining the prior isn't necessarily going to be suitable in that case without additional work for what that would look like. Of course, then one could impute the linear predictor, so just the normal part, then construct the constructions, and then use the classic G prior. And so it'd be interesting to see what would be the kind of the variance there, where perhaps even in the case where there non-normality, one might need to do transformations into some space, but then put the original the transform variables back into the model. So with that, I'll stop so that the other discussants have time. But again, thank you for a wonderful paper.
Thanks a lot, Merlise. And so we pass immediately the floor to Marco Ferreira for the second invited discussion. Thanks, Marco.
Let's see my slides.
Yeah.
All right. Thank you very much for the invitation. This is a great paper, and it's stimulating and inspiring. Missing data are everywhere, so this is very important. I just want to focus on some things that are important to be considered before practitioners start using this method. And there are two limitations that are because of the assumptions that are made. One is the MAR and MCAR assumptions. One limitation comes from that. And the other is, what if the true model is not among the models being considered? So let me just talk briefly about each of these things. So the MAR and MCAR assumptions. So these assumptions imply that the observations with missing dependent variables can be ignored. Is this always the case? And I think that's not always the case, right? So let me just give you an example. It's a very simple example. Say we have two regressors, x1i and x2i. Their IID normal 0, 1. And then the dependent variable is related only to the first regressor, x1i, through this simple linear equation, simple linear model. And then say that all of the values of x1i and x2i are reported. So there are no missing values for the regressors, but there are missing values for the yi's. Say that because of some technical limitations, values of yi larger than 2 are reported as missing. So now what happens is that the missing mechanism is not going to be of the MAR or MCAR types, okay? And this is a simple example. Maybe in this example, it's not going to be too bad to ignore the missing dependent variables, but in other examples that may be really serious. So in this example, we can see that we can compute what is the probability of missingness given the regressors that are observed, and we can actually then see that there is a relationship between missingness and the regressors. That relationship may be modeled, and that may actually improve the analysis, okay? Not only that, so what I'm talking about here is that modeling the missingness based on the regressors that are observed may give us information about what kind of missingness there is, and if the MAR and MCAR assumptions are reasonable or not. And note that, unfortunately, several times researchers discard data that they don't like, and that is not an okay thing to do. But if you look at the relationship between missing data and the regressors, you may gather information that may point to fraud in data collection or data reporting. Okay, another limitation is related to the assumption that the true model is among the models being considered. What if that's not the case? So here's an example, and I based this example on my experience with analysis of GWAS data, okay? So say that we have a dependent variable yi equal to beta xi plus error, but the scientist does not observe xi. Instead, the scientist observes two proxy variables, x1i and x2i. They are they are measurements of xi with error. Okay. Now the scientist tells you, oh well, I have these two proxy variables, and I want to know which one is the better proxy. And then the scientist decides to use a Bayes factor based on Zoner G prior to compare a model that uses x1i versus a model that uses x2i. And let's look at the base factor. So here's the plot of the log of the base factor if you compare those two models. The trouble is that those two models are equally distant in terms of Clyde divergence from the true model. And then we have what I call the M-open multiple optima paradox. So you can see that the log of the base factor comparing those two models is a terrible way of choosing which one of those proxies is better, right? Because they're essentially equally better or equally worse. So here, the log of the base factor is going to give evidence in favor of one of those two models 97% of the time. This is log base factor as you increase the sample size. So you see there's no convergence. This is not the way to go. Luckily for this regression problem, there's an easy fix. So instead of using base factors, we should look at all 4 possible models that use x1 and x2 and compare them using posterior probabilities. In that case, the posterior probability of the full model that contains both proxies will converge to 1, indicating that the better solution here is just combine those 2 proxies, which is like the intuitive thing to do. So luckily for this regression problem, it's easy to solve this Momo paradox, but in other problems like multi-scale modeling and choice of multi-scale models, it's not that easy to solve this problem, okay? Thank you.
Thanks a lot, Marco. And so we pass to the third invited discussant, Alexander Lai. Floor is yours. Thank you.
Can you hear me now?
Yes, nice.
Can you hear me? Okay, good. Sorry about that. Good. So, well, first of all, congratulations. Very, very nice paper. I really enjoyed reading it. So thanks for allowing me to comment on it. So this is joint work with a collaborator, I'll tell you. I'm going to focus on experiment 1 and the variable selection problem because it was quite a bit that they contributed. And this is quite simple, I can understand. So this is the model. This is the true data generating model. So you have variable 1, 2, 6, and 7. They are actually generating, they are active and those are not active. So this is their experiment. And I'm just considering a simple case. You have 40% missing at random. And there's correlation between these variables of 0.1. So they base their method on the Bayesian variable selection with missing data. And they select, they say this variable, this coefficient is active if the posterior model probability is bigger than 0.5. And they do that with sample size n is 100. And I was wondering, it's really cool what they could do. And what happens if we just do it over time? So we do it for 19, 20, etc. Just go sequentially. So I use that code, and then you see this. So this is for the coefficient 1 and 6. So they are below. This doesn't really matter. Come on, this is starting. We can start with the incorrect thing, but as you go a long time, you can see that you kind of fluctuate. So you have sometimes you say it's in, sometimes it's out. Well, these are the strong ones. These are in, so that's good. So that's what you expect.
Alexandra,
and he's
you're not sharing your screen.
No, I'm not.
No,
oh.
I can't see it.
I see the screen.
You can?
I see it.
Yeah.
Oh, it was there.
I'm sorry
Okay.
for interrupting. I don't know where it is then.
Can you see my screen still, everyone?
Yeah,
Okay,
I can
good.
see it.
Yeah, we
Okay,
can
sorry
see it.
about that. Okay,
Sorry.
good. So here you can see lots of fluctuations, and it's just what we saw, and then we thought, how can we solve this? And this is my colleague, postdoc at CWI. He invented something called, with some other colleagues, some sequential model confidence sets. So let's talk about those. So this is a subset of the number of models. We just indicate them 1 to the power of p, so that's 1024. Okay, and at time t, you have this collection of models for which it's smaller or equal than 1 divided by alpha with this beast here. There's some kind of exponential martingale And there's a tuning parameter in red that is, we set it to 0.3. This is number of models, about 1,000. And this is about all the time points before you hit T. So that T runs from 19, 20, etc. to 100. Now, here, this is some kind of score of a model. So the loss between model I and J. And for this, we used the base factor. We didn't think about missing data. We just used their code. So it's kind of like an easy comment to make. Okay, so they handled all the missing data. Now, for this exponential particle, there's something we can say about it. Well, there's the true model is in there, and these losses, they are some exponential in some sense. Then we can have frequentist guarantees that this true model is included in this confidence model set with confidence level 1 minus alpha. Or you can say if it gets out of it with less than alpha percent uniformly over time. Okay, so we take this set and then we just count the number of times that the variable is in, and that we can use as some kind of proxy to posterior model inclusion probability. Okay, this raw counting, we don't have prior model probabilities as in the real Bayesian setup. So this is a different data set. You can see lots of fluctuations. And if we use what we just discussed, you can see that it's much smoother here. So there's fewer fluctuations. Here you've got some problems, and that's kind of weird, but that's because we do raw counting. So one way to fix it is just make a mixture of the Bayesian version and the version we just discussed, and with some mixing here. And the mixing is just the number of surviving models. Okay, and it's if T goes to infinity, only the true model remains there. So this kind of outweighs the one we just discussed. If we do that, we get this nice separation here. So these are that's one data set we just did for many more data sets. And you can see that there's a few fluctuations that you can see. And this is the strong one, even less that. So, but here you can see many fewer fluctuations. That's quite nice. These are the number of fluctuations across totally, and is a histogram. So the blue one is what we just did with the mixed approach, and this here red is the standard naive way to do the Bayesian variable selection. At the end of the time, you can see that the numbers are quite nice, but we have sometimes more missing, or we include beta 4, beta 8 more than we should. But I wonder if that's okay or not. And to be honest, so what did we do? We just ran their procedure sequentially, very naively. I'm not sure if that's the way we should do it. Perhaps I misrepresented the procedure. That's very well possible. I'm not that smart, so that's what happened. Then we just went on, let's do a hackathon. Try to figure out, can we fix this somehow, or can we make it less fluctuating? And we kind of did, but it was really, it was just really hacking it. And we got a few fluctuations, but we had the cost of including variables that shouldn't be there at the end. Okay, but is that bad? Is that cost necessary? We don't know. And what's optimal? What's the fewest number of fluctuations that you get? And this last thing, we're talking here for Bayesian analysis, so optimal procedures, even sequentially, should be somehow based, and what we presented wasn't really based. So how can we get back to the base rule? Those are my questions. Thank you.
Thanks a lot, Alex. And so our last discussant, Javier Rubio. Okay, thanks, Javier. We see the screen shared. Hopefully Marco as well.
Thank you so much. Okay,
Thank
so
you.
first of all, I join the other discussants in congratulating the authors for such an interesting paper. So my comments are based on the invited discussion with Adam and Emmanuel Ogundimu. But I will also briefly mention the contributed discussion with Eric Chen and Jim Griffin. So the basic idea of the paper is to look at missing data, and in that setting, they have a regression model. So there is a response variable, and there are also some covariates. And so what they show, actually, Gonzalo just presented that under some assumptions of missingness at random, the missing outcomes do not affect the marginal likelihood. And so they can ignore it. But as Marco also mentioned, you have to be careful when there is missingness not at random in the response variable, because then that conclusion is no longer valid. So the authors focus on missing at random covariates, and they use this to develop all the proposed priors and using that the missingness is ignorable. But then we can also consider the case here when there is a missingness not at random in the covariates, and of course all the potential combinations of MAR and MNAR. So one point that I want to discuss here is a potential way to address one particular case of missingness not at random, known as sample selection, which is missingness in the response. Of course, there are many types of MNARs, and I will only focus on this specific type. And another discussion that I'm not going to present here is also accounting for the missingness rates in the covariates. So what is sample selection? So sample selection bias arises where the missingness in the outcome variable correlates with the outcome itself. And so this leads to something called non-random selection, which is a type of missingness not at random. And so, of course, when a subset of the sample is missing not at random, the sample that you end up with is not representative of the entire population, and the ignorability of the missingness is no longer valid. So what can do in this case? So if we assume, or if we are in a context where it is reasonable to assume this assumption of the sample selection bias, that the missingness in the outcome correlates with the outcome itself, then we can use methods to correct it. These are known as sample selection models. There are different ways to address this problem, but the most common originate in the 70s by Heckman. And actually they have some connections also with the skew normal distribution. So sample selection models are basically formulated as two equations. So we have an equation for the response of interest. In this case, I'm focusing on continuous outcomes, so just to connect it more directly with the paper. And we have also some selection process that we will also model with some covariates. And so we have two errors in these two equations. And the way to incorporate this assumption that the outcome and the selection are correlated can be done by assuming bivariate normal distribution, but of course you can use a more complex model to capture the relationship between the outcome and the selection model. So this assumption leads to a very tractable livelihood function, which basically looks like a linear regression model with a probit model, something similar to what Marco presented, and it also has a very close connection with the skew normal distribution. So the question is, which variables do we put into these two models? So to explain the outcome and to explain the selection process. So we can see this as a variable selection problem, which starts connecting with the paper itself. And this problem has been addressed recently using adaptive lasso methods. And more recently with our students, we also consider variable selection, Bayesian variable selection using spike and slab, local and also non-local priors. The limitation, of course, is that we have only addressed the case where there is sample selection, but not the case when there is a missingness in the covariates. So one potential way to address missingness in the covariates, if we are willing to assume missing at random, is to use the proposal by Garcia Donato et al. And then just simply connect the two extensions. So we use a sample selection model for the sample selection and their methodology for the missingness in the covariates. But then, of course, this is not straightforward. So some subtle questions will be like, should we use different priors for the selection and the outcome process, or is it better to use a joint prior for the entire vector of regression coefficients? And the more challenging case is what happens if we have sample selection in the covariates, but maybe we also have some type of missingness not at random in the covariates. So the idea is that we find the paper very interesting. There is a potential application to address the case of missingness not at random, but of course this opens the door to looking at more diverse types of missingness mechanisms. So these are the references that I mentioned throughout, and thank you so much for your attention.
Thanks to you as well, Javier. And so now it's time to pass the floor to Alicia, who will
Thank
make
you,
the
Milo.
rejoinder of the...
Sure,
Thanks a lot.
I'm going to share my screen.
Yeah,
Okay.
we can see it. Thank you.
So, hello everyone, and thank you for joining this webinar. Let me start by expressing our sincere gratitude to all the discussants for their insightful comments and valuable suggestions. Their work has certainly enriched our paper and opened new perspectives for future research on this topic. It is a great honor for us to have received so many discussions. I must apologize because the entire content of the rejoinder will not fit in this 10-minute presentation. We have identified several topics that have been addressed by different discussants, such as the missing mechanism, the prior distributions, or the imputation model. Today, I will give a short overview of our rejoinder. The audience can find all the details in the written response. The first topic I would like to address is the missing data mechanism. Several discussants were interested in addressing problems where the MAR assumption does not hold. Our research provides useful guidance on how to tackle problems subject to missing not at random. In fact, the MAR assumption is introduced in section 3.2, and we show that it implies the ignorability of the missing data mechanism. Nevertheless, we fully agree that incorrectly assuming MAR may lead to serious consequences. Using the example proposed by Ferreira, we illustrate that ignoring missing not at random could throw away the potential discriminatory power contained in the missing data mechanism. Perizzi also highlights the utility of the approach to handle uncertainty in the missing mechanism. This was not our original focus, but we have explored this possibility in example 3 of the rejoinder. Both Rubio and Ferreira state missing not at random problems affecting Y, with clear reminiscences of survival analysis. In example 2, we show the connection of our work with variable selection in survival analysis. We also compute the marginal for the Heckman sample selection model studied by Rubio and collaborators, what opens the door to addressing this problem within our framework. Bianco and Klein emphasize the consequences of ignoring missing not at random in spatial applications. Their simulations show that our method performs well, even compared with a subjective approach. Tomodakis and Zoufras raise an important concern about the potential bias when the outcome variable is excluded from the imputation model, when the missing data mechanism depends on the observed response Y. We have replicated the simulation study to conclude that using Y in the imputation model induces a spurious correlation with non-active covariates, especially under the null model. Let's move on to the second issue discussed by Ferreira. As a variable selection method, our proposal inherits the gamma open problem. Ferreira denotes those by M open, but we choose gamma for this notation, sorry. Ferreira's discussions illustrate the Momo paradox, which also affects our methods, although it is not specific to missing data. He suggests a solution, including all possible combinations of variables in the model space. In any case, these questions made us think about the possibility of artificially copying an observed variable if we had a large percentage of missing values for one variable closely related to another via imputation. In such a situation, it is possible to generate different models that are at the same distance from the true one. Arnold and Lee explore a possible extension of our proposal to the setting of sequential analysis, a framework of interest in applications such as adaptive designs. We are pleased to observe in figure 1 of the discussion that our method provides the expected results. It chooses active variables even with limited data and becomes more decisive as information accumulates, meaning that the inclusion probabilities of active variables tend to 1 and that of non-active variables tend to 0 as the data or n grows. They explicitly note that the sequential model confidence sets are frequent tests. The Bayesian posterior model probabilities instead quantifies data-informed beliefs about candidate models. Comparing Bayesian variable selection outputs is a general challenge in model uncertainty, extending beyond the specific issue of missing data. This has been previously addressed by Cabras for large and non-explorable model spaces. Several discussants, as Clyde, focus on the prior distributions we developed on related ideas. As suggested by Perizzi, the G-prime prior can be used in a fully observed data setting, constituting a more palatable alternative to the G-prior, as described by Clyde. According to María Eugenia Castellanos, the G-prime prior is more Bayesian than Sendler's original proposal. We are convinced that the comparison of the G-prime prior and the G-prior is a fruitful line of research. For example, the matrix sigma sub gamma gamma in the G-prime prior will be informed by all covariates in the dataset, as opposed to X transpose times X, which only use those in model gamma. Perizzi describes the ability of the G-prime prior to predict new outcomes when the associated covariates are unknown. We have proven that the distribution of interest can be obtained by integrating out X super n plus 1 with respect to its marginal posterior distribution. Perizzi has raised the possibility of using a hyperprior on the parameter G prime. Fortunately, Ehidi has further developed this possibility based on the mixing distributions proposed by Liang and collaborators. His formulas clearly show the added computational complexity. A similar extension is sketched by Consoni and Foskakis, who propose using the shifted generalized beta prime distributions as the mixing distribution for G prime. We add to this discussion the possibility of considering the mixing distribution associated with the robust prior by Bayarri and collaborators. Consoni and Foskakis have raised the related topic of intrinsic priors with missing data. We agree with the discussants that our framework provides a compelling starting point to address it. Mulder introduced an alternative objective Bayesian method based on the fractional Bayes factor. His results demonstrate that the two procedures lead to remarkably similar conclusions. In the Rejoinder, we illustrate the practical challenges of implementing fractional Bayes factor in problems involving missing data, including the always problematic definition of B, which becomes even more challenging with missing data. Several discussions highlight the issue of model misspecification for covariates when they are assumed to be normally distributed. However, our proposal does not assume normality until the results section. What is assumed is that the variables are quantitative and that their mean and variance-covariance matrix exist. As said before, we presented a simulation study which showed that using multivariate normal model for clearly non-normal covariates hampers the performance of our method. However, we did not explore this issue in much depth. We are very grateful to Franzen for proposing an example that clearly illustrates the problems at hand. Inspired by his example, we have added a simulation study to show that the inadequacy of the imputation model could hinder the model selection procedure. In our conclusions, we acknowledge that assuming that the covariates are quantitative is one of the limitations of our work. Both Clyde and Chen, Griffin, and Rubio propose hybrid methods using non-Bayesian models to address this issue. While these proposals might be interesting from a practical point of view, the proposed methods do not provide a joint distribution for the covariates. By contrast, G and collaborators and Steele and Sense not only provide a joint model for the covariates, but also circumvent the assumption that the variable must be quantitative. Steele and Sense proposal of using latent Gaussian models for X offers great flexibility in accommodating different types of variables and distributions, while enable the direct estimation of two central parameters in our proposal, mu and sigma. McKicken's thoughtful and inspiring discussion is, in our view, a must-read for anyone. He reflects on the importance of carefully considering the structure and the purpose of a model. However, it is not straightforward how to focus on the modeling structure when the set of active variables is not known, particularly in scenarios with a large number of potential covariates. For this reason, we opted to keep our framework as simple as possible, aiming to facilitate its extension and broader applicability. Regarding the proposal of splitting the data into training and testing sets, it raises the questions of which error measure should be used when the goal is variable selection, and also on the details of its implementation. Apart from the review of the most discussed topics and some individual responses, we have conducted several additional simulation studies inspired by the discussions, which yielded some interesting results. I would like to close by thanking again all the discussants for the generous engagement. Thank you very much for your attention.
So thanks a lot, Alicia. It's a very nice rejoinder. I really liked it, the way you managed to actually reply not just to the invited discussion, but also the contributed discussion. And very nice. So yeah, we had a record number of 11 contributed discussions. And well, we had already a very broad discussion. We are a little bit over time, not that much, which is great. So if there are some further questions from the audience, I think we can take them. Let's see, we still have a lot of participants. If there are not, then I think we can close this webinar, and let me thank again all the authors for the very nice presentation, all the discussants, and I think it's a great paper. And as said, I mean, read it up. It's in the advanced section of Bayesian Analysis, and will come out in the December issue, which will be published shortly. And that's it. So thanks a lot. Thanks to everybody. It's been a pleasure, and hope to see you all soon. And thanks to everybody who attended. Thank you.
Thank you.
Thank you very much.